I just didn't want to get the roll call on it. That was what it was. Okay. So to repeat, what we're going to do is we're going to go over a couple of questions from the second quiz dealing with scheduling algorithms, and specifically I'll go over the sort of steps in the algorithm itself, but also I'll talk a little bit about the computation of turnaround time and waiting time, because I asked about those, but I feel like people struggle with that, which is probably an indication that I need to spend more time on them, because I really glanced over them. I will admit that. So I'll do that, and then I'll walk through on the homework the priority inversion scenarios and the rate monotonic and EDF scenarios, so that you have a chance to ask questions about them. You have a chance to say, no, you're wrong, or just ask why things are working the way they are. Okay, and then I'm going to go through a PowerPoint that is the listed topics that are covered in the exam. I'll stop on the bullet points so they just don't read through them and just ask if people have questions on them or maybe give an example. But really, it's just designed to be a reminder of things to study. There's a lot in those textbook chapters that I'm not really holding you responsible for. So I just want to make sure that you have a list of the things that could appear on the exam. If we have time, then we may go back and restart the Linux stuff. If we don't, we'll do that after the exam, and the session after the exam. The exam will take up the entire class time on Tuesday. Okay? All right, so homework, or quiz 2. You had a question like this. Given a round-robin scheduling algorithm with 4 processes of these varying sizes and these different quanta, how do they work out? So what I'm showing here is just, the way I marked it here. It makes it easier to compute turnaround time if you list the end time for each process. Now, some of you went ahead and listed each time unit being executed. That's perfectly valid. This is a little simpler to me to go ahead and summarize, P1 ran for 3 time units here, right? Because that's the length of the quantum, Q equals 3. And we're doing simple round robin, so we don't have any questions about what's the sequence in which we execute these things. It's just the sequence in which they're listed. We just shift from one to the other. So P2 then executes until 7. So why, if there's a quantum of 3, why am I showing it until 7? Context switching, right? And pretty much everybody got that. So that was great. But if that's the case, then, and so you can pretty much see a pattern, right? That most of the steps are going to be execution times of quantum plus 1, right, for context switches. So it's usually pretty stepped, except when you get to those last points where the process is finishing up. So some of you thought on the exam that if I reach a point where my process would finish, I still run the entire time quantum. But this is really a place where it kind of indicates that's not the case, right? So right here with P3. P3 finishes at 21, which is only 2 time units after it starts, with 1 time unit for context switching. That's because it didn't use up its whole time quantum. When a process doesn't use up its whole time quantum, the CPU doesn't sit idle, because there's several ways of giving up the CPU, right? One is to yield. The other is the CPU stops you, for instance, with round robin, and switches. Okay, so I also, on the last entry, found it easier just to combine, if I had a process running at the end, as we did here with P4, to combine all the remaining time into one cell rather than to show different cells. One of the reasons for doing that is I want to make sure that everybody understands if a process uses up a time quantum and there's no process at the end, never switches. If there's no ready processes in the ready queue, there's no switch time, there's no context switch time, the process just keeps running. And so even though there might be a brief time interruption, it's negligible. Because there's no context switch time, because there's nothing in the ready queue. Any questions on any of that? So now what's turnaround time? Somebody define turnaround time for me.
Time it takes to complete a process.
Absolutely, time it takes to complete. So that's going to be, it's going to start on arrival, and it's going to run to completion. right? This is one of the simpler ones. Now, the question asks you to compute turnaround time. I'm sure you guys were focused on the schedule because very few people actually did that. But just be aware on the exam, oftentimes I'll show you one of these and I'll say, fill out the schedule and compute this, right? It's going to be either turnaround time or waiting time. I'm not going to ask you to compute any of the others. I'm not going to ask you to compute throughput or anything like that. That's exactly right. So it's pretty easy in this case because I've listed all the end times. So you can just see P1 completes at 19, P2 completes at 7, P3 completes at 21, P4 completes at 26. It's pretty straightforward. You can see with a time quantum of 1, it's more the same, right? Usually the steps are in 2, context switch time plus quantum. And here's all the turnaround times. You notice they're a lot longer. Why are they longer? Why does it take longer to complete? You're switching so much. You're spending so much time switching. This is an illustration of the point that many of you made, and correctly, in an answer on the quiz when we talked where you were asked about, well, what if your time quantum is too small? Well, if your time quantum is too small, you're going to context switch too much. You're going to thrash. And then here's one where the time quantum is relatively large, a quantum of 6, right? And in that case, it's more like first come, first serve. Okay. Any questions on that? All right, I'm going to go over one of these for, actually I'll go over both the preemptive and non-preemptive shortest job first and show the computation of average waiting time. You had a question like this on here. In this case, one of the things that was different here is we had, once again, 4 processes, 4 different burst times or execution times. But what is a little different here is that we had different arrival times. So let's go through the schedule first. P1 is the only process available to run at 0, but that changes at 2 when P2 arrives. And so what happens there? Preempts. And why does it preempt? Run that by me one more time.
A lower burst time?
Yes, that's exactly right. That's right, Justin. Lower burst time. So it preempts. P3 then arrives at 4, and it's going to preempt because it also has a lower burst time. It completes, and by the time the scheduler has to make a decision again, it could choose either P2 or P4. And we just by convention say we choose P2 because it was the first one we started running. It's earliest in our list, so we're just conventionally going to choose P2. And so, in any case, it's a pretty clear sequence of events. It's preemptive, shortest job first, right? The job with the lowest burst time in the ready queue is going to run, and it's going to preempt if there's a job on the CPU with a higher burst time. So computing waiting time. This is kind of showing the waiting time here for the different cells. That's one way of looking at it, right? When P1 starts off, it's waiting for 0. Next time P1 runs, it's waited for 10 more. Why 10 rather than 12? Some of you did something like this on your exam. Why do I say the wait time for that next execution is 10 rather than 12? Because it ran for the first 2. Absolutely, right? So if it's running, it's not waiting on itself, right? That's not time it's spent waiting. We're only counting time you've spent waiting. So that's exactly right, Charles. All right. P2. Same deal. Even though it arrives at 2, it's got a 0 wait. Even though it doesn't start until 2, it's got a 0 wait time because it arrived at 2. So again, wait time is going to be measured from arrival to completion. You're gonna look at the time you waited. So you got to be careful if you get a question with different arrival times to make sure to subtract out that arrival time. And then this is just more of the same, right? Where P3, even though it starts late, actually didn't wait at all. It started executing as soon as it arrived. So another way of looking at this is to look at wait time as finish time minus arrival time minus execution time. And this just illustrates how the computation comes out the same. So you get a total of 15 divided by 4, an average wait time of 3.75 time units.
P2?
Yes.
Why is it not this?
Because it executes again. P2 gets preempted by P3. Yep, good question though. Okay, so now we get to non-preemptive, and there's a little, it's easy to be lured in by this question. Non-preemptive, again, you start off going cell by cell, and the only possible choice is P1. It's the only one that's arrived. Because this is non-preemptive, however, once P2 arrives, it doesn't, even though it's got a shorter burst time, it's not going to interrupt P1. P1's got the CPU, it's going to finish. So the same thing is true for P3 and P4. So by the time the processor frees up again, when P1 is finished, you've got 3 processes waiting in the ready queue. It would be easy to assume, oh, okay, well, P2 should run, right? This is non-preemptive. Well, except that now what's happening is you've yielded the processor. Even though this is non-preemptive, it's non-preemptive shortest job first. So you actually have 3 processes waiting in the ready queue. You've got to make a choice. Which one of those, by shortest job first logic, should run first, which is why P3 runs. So it goes P1, P3, P2, P4. So it's a little different than you might expect. You kind of think non-preemptive, it's sort of like first come, first serve, but it's really not. And that really illustrates the difference, the fact that P3 runs second here. And the average waiting time is just more of the same then. It's the same thing of make sure it's finish time minus arrival time minus execution time. You can see our wait time is a little higher because it's non-preemptive. And this just kind of is more of the same in this last question. This is first come, first serve. I'm showing here the start times. So if you were to compute average waiting time, this is how you would do it. You end up with an average waiting time of 12. Any questions on?
No question. Can we just have it posted that quiz keys posted on Blackboard?
I'm not going to post the quiz keys, but if you've got questions on specific questions, I'll answer those, and you can fire them off to me. I don't like posting keys out there. I just don't want the entire quiz out there. But you can see it's out, these key answers are out there. If you go back to your quiz and you see a question, if you've already got the question right, then you've got the key. If you see a question where you're like, why did I get this wrong? He's wrong, then send me an email and I'll respond to it. If I get a lot of emails about a particular question, I'll post that.
Is test going to be like quizzes?
That's a great question. And I'll get into it a little bit more when we talk about the exam review, but the short answer is yes. It'll look a lot like quizzes. Not entirely, but a lot. Okay. Homework. Okay, so these first questions were all about priority inversion. And one of the things that's easy to happen on these questions is you can start trying to fill that chart out and go too fast, right, to try to get through it. It's really good. It's really a good idea as you go through this, if you're wondering about something, to pause for a second and make yourself go step by step and answer the question for every single time unit. Why is this process running rather than another? Okay, so our scenario, kind of complicated, right? Even though we've only got 2 processes, one of them, T2, arrives at 0, T1 arrives at 3, and then you've got these 2 resources in play, A and B. And the sequence in which these guys request these resources is different. So T2, which is the first arriving process, is going to ask for A first, after 2 time units, right here, and then B, after 3 more time units executing with A. Some of you asked at that point, at a point like this, let's assume that it got both of them. We'll see in a second that's not the case in the first scenario. Let's assume it got both resources. You asked, well, gosh, does it have to release this A to execute with B? No, they execute at the same time. Of course, one resource, A is still released according to the time units for A, right? It may be released earlier than their joint time together. So they may only have a small intersection of time where they execute together, but processes can absolutely have more than one resource at a time. You don't release the resource just because you get another resource. Right? We saw that in some of our, remember our dining philosophers with the 2 utensils, right? And you remember how they could get in trouble with those 2 resources because they had 2 resources in play. And the 2 resources cause us some problems here. Let's see how that works out. So who's going to execute first? Well, T2 is our only choice. And until T1 arrives at 3, at the 3 tick, that's right here, right? Until it arrives, starts in 3, T2 is gonna run. So T2 runs for one time unit, 2 time units, but we see that T2, after 2 time units of running, as just a task, is going to request and obtain, in this case, because nobody else has it, resource A, which I've now noted in green as a critical section, right? So it gets resource A. Now T1 arrives, and why does it preempt? I mean, T2's got a resource. Sorry, that sounded like a lot of people said it's a higher priority, right? It's a higher priority. If T1 has got everything it needs to run, it's going to run because it's a higher priority task. And remember, especially here, there is no logic to change task priority turned on, so to speak, for this system that we're talking about, based on resource ownership. So T1 is going to preempt. Some of you, I saw some questions where you then return to T2 in the next cell, the next time unit. So let's ask the question, why there's no reason in that next time unit to switch, because T1, again, has everything it needs to run, and it's a higher priority task. So it's going to continue, and if it never asked for a resource, it would execute it its entire time. But now it asks for B. But that's okay, because B isn't owned by task 1. It's not locked. It's available. So T1 can get B. And that is what it proceeds to do. So here it is. It gets it after after 3 here, right? It runs for 2. But why does it switch here? Because it requests A. And why does that matter? Because T2 has A, right? It's locked. So that's where priority gets overridden, because it can't run anymore. Task can't run if it can't acquire the resource it needs to continue. So it's going to yield the processor. It's going to wait. We saw with some of our synchronization mechanisms, right? Mutexes, semaphores, whichever it's using in this case, and we say a mutex. As it asks for the lock, if it can't obtain it, it's gonna wait. That's the way those things work. So it's going to release the CPU, and T2 is the only process left to run in this case. So T2 is going to start running 1, 2, and we say here after 3 time units of running with A, T2 is going to ask for B. What happens? So mass hysteria, right? Or in other words, a deadlock, right? That's what we have. We have a deadlock here, and that's what happens with when you get more than one resource in play, right? Is you can get a deadlock because T2 needs a resource that T1 has, and T1 needs a resource that T2 has, so they're stuck in a circular wait. That's bad. All right, so you notice the first question said, hey, does a priority inversion happen? Yes, it happens here, right, at 8, because T2 has a lower priority, and yet it takes the CPU back only because T1 can't go any further. So we got a priority inversion. So then question 3 says, hey, is there any other problem? Hint, hint. Is there anything else bad that went on? Yeah, we've got a deadlock. That's pretty bad because now neither process can complete. Okay, can priority inversion resolution, such as priority ceiling and inheritance, help to solve the problem? Well, let's see, shall we? So here we are. We look a lot like, up to here, we look a lot like we did already, right, in the first question, with no priority inheritance turned on. What happens that's different is that at this point, T1 asks for A, which is the resource that T2 has, and now logically at least, T2 the priority of T2 is hoisted or elevated above the priority of T1, logically. And yet, what happens? It doesn't help out, right? We execute 2 more times, and we still are in the same situation. We ask for B. It doesn't matter that I've got a higher priority. I can't wrest control of that resource from the other task. I can't wrest control of B from T1 any more than T1 could wrest control of A from T2. We're deadlocked. We're still deadlocked. So one of the things this points out is that if you have a lot of resource contention, and this is something that the slides emphasized, if you have a lot of resource contention, priority inheritance may not be enough, especially if you've got multiple resources in play. We'll see when we talk about deadlocks, it's when you have multiple resources in play that are potentially claimable that you could have deadlock scenarios. Remember our Mars Pathfinder scenario, we didn't have a deadlock, we just had in effect a timeout because it was only one resource, that communications bus, that was involved. But if you get 2 involved, you got to at least be aware of the potential for deadlocks. And one of the things the slides say is that priority inheritance may not fix deadlock problems. Why do you think that is? Let's go into priority ceiling. I'll ask that question again. So priority ceiling, however, looks a little different. Priority ceiling, well, looks more than a little different, right? Because T2 starts executing, and as soon as it requests A, its priority is elevated. You can see we've got a priority line representing logically the priority level of the resource. The resource itself, of course, is not running, but it can, in effect, loan its priority to a task that requests it. That's what happens to priority ceiling. And you can see we're at the ceiling, right? We're above any other task, which in this case is just one other task, that could run with the resource. So what happens here when we get to the arrival point is that we don't switch. We don't switch at the arrival point for T1 because the priority of T2 is already elevated. It's elevated earlier. It's elevated as soon as T2 requests the resource rather than as soon as a higher priority task requests the resource. So because we get elevated early, now when I go to ask for my next resource, B, I do get elevated to an even higher priority because B has a higher priority than A. But I continue to run. I complete my run. And now I go back to T1. As soon as I get done with my resources, I don't just continue executing at that high priority. As soon as I get done with my resources, I'm back to my own priority, in which case I get bumped by T1. T1 itself, because it requests B, gets a higher logical priority. So we're just showing, even though it doesn't need that in this case, this is just showing that it's really elevating or really executing at this higher priority. At this point, it releases B, it goes back to the A level of priority, and then it completes its run, and finally T2 completes. So now, why is it that you think priority inheritance might be susceptible to deadlocks more so than priority ceiling? That's exactly right. Because inheritance waits. So to get back to some of the points made in the slides, that's why if you've got a lot of contention, inheritance might not be enough. If you don't have a lot of contention, inheritance might take care of your sort of oddball cases of priority inversion. Or if you've only got one resource to worry about, right, then inheritance might take care of it for you, as it did for Mars Pathfinder. Any questions on any of that?
Yeah, that's what the top what got me was A didn't let go of A, it kept A, and then it wanted B too.
Yeah, it's greedy.
Why wouldn't it let go of A if it was done with A?
It wasn't done with A.
It says it's done with A.
Tell me where.
At the end of it, you ran it for 3 ticks, right? And then it wants B.
Tell me which one you're.
T2 on the first or the second.
The first one, okay. So T2 asks for A here.
Yeah.
Critical section for A takes 4 time units, and the critical section for B takes 5 time units. So that little bullet is saying you got to run with A for 4, and you got to run with B for 5, from whatever time unit you start with. So it's not done with A, because it's still got 3 more time units to run with. Does that make sense? Okay.
For priority ceiling, could you show me how it runs for all the time units of A and B? Because I'm having a hard time reading that part.
Okay.
I can't tell.
Let me do this first of all. Is that helping?
Yeah.
Is there a specific area that you want to know about?
How is it running for all the time units of A and B?
Which one? T1 or T2?
Both.
Okay, let's start with T. Let's start with T2. We said A runs for 4.
Yeah.
With both processes run for 4 with A and 5 with B if they request it. So let's count them off. I run with, if I can find my mouse pointer again. I run with A, 1, 2, 3, 4. And I've requested B according to the scenario, right? So this is one cell where I run with them jointly, right? And but now I'm done. So this what I've got indicated here is minus A. I'm not running with A from this point forward because I've executed for 4. But I get B here. 1, 2, 3, 4, 5. Stephanie, does that answer your question?
Yeah, a little bit.
Okay.
So
Sam?
I have a follow-up on that. So I understand now like how this reads, but how come in the priority ceiling they're able to run jointly?
You can, you can run jointly. If you hadn't had a deadlock, you could run jointly in the other scenarios. The reason they can't run jointly in the other scenarios is they have mutually exclusive locks.
Okay.
That's why.
Got it. Okay.
So there's absolutely nothing about those scenarios in terms of the priority logic that would prevent that.
Okay, so T2 could actually have B and A running at the same time.
Absolutely.
If T1 hadn't already hogged.
Right. Let's say we change the scenario so that T1 arrives at what, 5 or something like that. I'm thinking 5 or 6, right? You wouldn't have a problem at that point. I mean, you'd have some delays. You might have some delays for T1 while it waits. It would probably preempt it. I think at that point, T2 would probably have A. T1 would still preempt until it asks for B, and then you go back to A. It would run. Go back to T2. It would complete with B, and then T1 would run its entire run.
Okay, that clears everything up for me.
Awesome.
So the other one is not protected by the mutex scenario.
Show me when you say the other one.
The ceiling one.
The ceiling absolutely has mutexes, but they're never mutually exclusive. I'm sorry. There's never a point where one process is asking for a resource that is held by another process. And it's all because of the magic of the scheduling hoisting, the priority hoisting. So T1 never even starts to execute until here, because as soon as T2 asks for A, right, its priority gets elevated already above where T1 is. T1 can't preempt it. So A is able to complete processing, sorry, T2 is able to complete processing with A and then release A. So in mutex terms, we lock, we unlock. So at that point, A is already unlocked. We lock B, we unlock. So A and B have both been locked and unlocked before T1 even starts. So even though they both acquire mutexes, they aren't locking each other out because of the time span in which they're asking for those locks. Does that help? Okay. It's not a simple scenario. You'll see you'll see something a little like these scenarios on the exam. So if you're still a little confused about it, ask questions. I mean, do whatever you need to get straight on this. Okay? And if you think of questions as I go on here and want to re-ask them, then feel free. All right. I'm going to shrink this back here.
Are you not posting this either on YouTube?
I think for these priority inversion ones, I'll post the run. How about that? Because I know those are these are probably some of the more challenging ones for the semester. Okay, just so you can study them and get to know them, because the scenarios in the exam are not the exact same scenarios. They're just okay. So here we have, that was priority inversion. These next scenarios are two different forms of scheduling, right? They're rate monotonic and earliest deadline first. And it begins with this computation of the utilization bound and then the usage of that to determine if it's conclusively or inconclusively schedulable, right? So we have three processes in play here, T1 through T3. We compute the utilization bound. You can see we have these handy hints up here that said, hey, you don't have to do this computation. Here's what your figures are, right? So this comes out to 3 times 1.25 minus 1, or 0.75. If you actually did the math, it would be slightly different than this, but you know, I'll take either answer. I thought it was easier to have a rough approximation for purposes of this question already in your homework. So if you'd be conclusively schedulable if you were below that bound, less than or equal to that bound, right? So, but you're not. What's your utilization? Your utilization when you compute is actually 0.96. So you're in a maybe schedulable, maybe not realm, right? You are here. You're greater than the, you're less than or equal to 1, but you're not less than or equal to the utilization bound. So let's look at rate monotonic. Anybody want to tell me what rate monotonic is?
Everyone else can say that.
Okay. Sharon, were you starting to say something?
Shorter priority is higher.
Yes, the end. Well, yeah, that's exactly right. Right. Your priority is the inverse of your period. So shorter periods have higher priorities. That's exactly right. All right. So we start off and we got T1 arrives at 0, T2 and T3 arrive at 3. Their periods here are 3, 7, and 5. So what's our priority ranking if you had to rank these guys?
T1, T3, T2.
Correct. That's exactly right. So T1 starts off. Here we are marking, the way I mark this, you may mark it different, is the T1 period here ends here to the right. T2 and T3 arrive. So at this point, all of them are available to execute. But as Sharon just explained, our top priority process based on rate monotonic is going to be T1, followed by T3, followed by T2. But T1's arrived again. T2 hasn't finished. Both T1 and T3 are only 1 time unit long, but they arrive pretty frequently, right? Their periods are pretty short. So T2 starts to execute, But T1 has arrived here, so it interrupts or preempts.
Question. So on the deadline then, Matt, because so there's a deadline there, right?
Yes.
So deadline for T1 is every 3.
Yes.
That's why there's T1
Yep.
there, 0, 1, 2.
Yep.
Okay.
Yep, that's exactly right. So there's both a deadline and a period, right? So that means I come back and I get in the, effectively when your period is over, you get back in the ready queue, right? That's you're ready to execute again. Which is why T1 is ready to execute here, and it's going to preempt. So another thing it asks for you to do, the question is count the preemptions. It's going to preempt T2, which is currently running. It is not finished. It's 3 time units long.
Okay, so if it's every 3 for T1, for example, so we mark T1 on 2, 0, 1, 2. Now we mark the second deadline is 3, 4 on 5. So I don't know how does that work? Like, do we count 2 as 1 unit, or do we count the next? I'm not making sense here.
No, I understand. So yeah, so it arrives every 3,
Right.
right? 1, 2, 3,
Right.
it arrives here.
Okay.
1, 2, 3,
Okay.
it arrives here.
Okay.
And so what can get a little confusing because I'm doing this in Word, you know what would be clear, you'd probably have fewer questions, honestly, is if these were marked on the ticks. If they were marked on the ticks, you probably wouldn't have these questions. So it's a compromise for Word right here. You might find it, when you're taking the exam, easier to mark on the ticks. I think it reads a little bit more cleanly, and there's a little bit less of you as you're trying to juggle 4 different things, trying to say, okay, is that, I marked T1 here, does that mean it's the deadline or period is to the right or to the left?
Right, yeah, that's because I was wondering about that, because you counted 0, 1, 2.
Yeah.
Then in my mind, I'm thinking you should count 2, 3, 4.
Right.
And that's just.
Yeah. So I start here. And I return, I'm done, right? I only have 1 time unit. I return to executing T2, and yet my deadline for T3 is along this line. So now I've got T3 ready to execute along with T2. T3 is a higher priority, so it preempts again. Meanwhile, T1 arrives here and is available to execute in this cell. So T1 is going to arrive. Why don't I mark that a preemption? Because T3 is finished. So no process really owns the processor at that point. And the scheduler is asking the question, what runs next? Because there's no process on the processor. It's not interrupting a currently running process. I go back to T2, but I'm over the deadline, right? I missed the deadline here because I got interrupted so much. And really, this is just more of the same throughout the rest of this question. Any questions on rate monotonic? So I miss a deadline with rate monotonic here. Remember, I'm skirting pretty close to my maximum CPU usage at 0.96. When I looked at the sum of the utilization, I'm asking for this device, whatever it is, to use a whole lot of the CPU's total capacity with the task that I'm trying to run on this thing. Go ahead.
I feel like I don't completely understand at all, because I don't know, because for some reason I feel like I don't know how to explain it, because T1 ends at 2, so I don't understand. Does it have to run for like 3 times before T1 of 2? So is this just a case where nothing is ever going to get completed because it's just going to constantly be interrupting each other? Or something, because T1 occurs and then nothing happens at 1 for some odd reason. Nothing happens at 2 for.
Well, let's talk about the odd reason. Let's start there.
Back.
Why does nothing happen at 1 or 2?
I'm guessing because it just doesn't run because things are stupid, and so and so it doesn't. And then T2 and T3 arrive at 3.
Okay, well that's a possibility, but let's talk about the reason nothing runs. Who can tell me why nothing?
Wouldn't
Sam?
it be because since T1 arrives at 1, but it has an execution time of 1, since there's nothing else going on, since 2 and 3 aren't there, it's not going to run anything in 1 and 2.
Exactly. It's done. Remember, the period is not necessarily equal to the execution time. That's why these are in two different columns here. So the execution time, it's only going to run as long as it has to run to finish its execution. It's not going to run for its up to its deadline necessarily, right? Just because nothing else is running. There's nothing to do. There's nobody to use, think of a computer that's a shared resource. There's nobody to go, nobody needs it. So it's not in use.
But then how will it ever meet its deadline? Because it's always going to come back after the deadline has already passed, so it can never meet it.
It met its deadline. T1 met its deadline.
But I thought when it meets its deadline that it no longer occurs.
No. These are periodic tasks.
Yeah.
These are periodic tasks. So good. I'm really glad you asked that question. These are periodic tasks. So the idea of a periodic task is going to be every time the period for the task, that's the point of these period numbers here. Every time my period runs, think of that as like the task schedule. That's really the schedule for the task. Every time that period restarts again, you got to run that task. At some point, you got to start the task after the period starts and finish it before whatever the deadline is for that period.
So it just has to run to meet the deadline, but it doesn't have to complete.
It doesn't have to keep running after it's done, right? Yeah. So this task is saying, hey, I've already handed my assignment in. I'm done, right? I'm not going to continue to burn CPU. I've got nothing to do. But I did meet my deadline because I finished. The question is, do I finish before the deadline? So Stephanie. Okay. Well, this is good. I'm glad that these questions are coming out because you'll see something like this again on the exam. And this also helps me to understand where it's not going to help you much, but where next go round to clarify and make sure people understand the importance of what a periodic task running every period, but not using up the entire execution time if it doesn't need it. So if these were really conclusively schedulable, one of the points here is the point of this utilization bound is it's not just a math exercise. The point of it is to say it's saying something intuitive, right? Which is if I have a lot of different tasks and they all have hard deadlines to meet, the more of the CPU that my total tasks use, the more of a chance is that I'm going to miss some deadline somewhere, right? So we've got really crowded tasks here. And Stephanie asked, well, gosh, it seems like they're always going to run into problems. Well, when you're at 0.96 using rate monotonic, there's a decent possibility you might run into a problem unless you're really careful because you're right at the point where you're close to 1. You're close to using all of the CPU's capacity. And one of the points that the textbook makes about rate monotonic is one of the problems with it is it tends to not use all the CPU, right? To be conclusively schedulable, you'd have to say, you know what, I've got to have tasks that only sum up to using the points approximately 0.75, 75% of the CPU's capacity. Sandra, do you have another question?
Oh, never mind. I was going to add something to that, but I changed my mind. I'm good.
Okay. All right, so these are great questions. Things change a little bit. We talked a lot. I marked each of the preemption points with a P because I thought that was an easy way.
One more question.
Yeah, sure.
So on the arrival on T2 and 3 is at 3. When do you mark the deadline? Does it still start at 0 or 3?
The deadlines restart. So the length of the deadline in this case, it should be the same as the period, and it is, right? Because we're dealing with that kind of schedule. So the length of the deadline is the deadlines restart as each period restarts, which is why deadlines are marked throughout here for the different processes.
Right. So T2 for T3, for example.
Uh-huh.
So it starts. So that's when you start counting is at 3, where they begin, right? And then
Yes.
Okay,
Yes. Right. For the ones that don't arrive at 0, you're going to start from their arrival,
Right.
not from the start of the entire.
Okay, I just want to.
That's a great. I'm glad you asked that.
So would 4 not be a preemption since 2 and 3 came in at the same time, and 3 pushed 2 out of the way?
Yeah, that's exactly right. Why is 4 not a preemption? It's because let's take it a cell at a time. You've got the logic exactly right. Cell 3. Now, I've got 3 processes in the ready queue. I'm just making a scheduling decision. There's no process running here. And so I'm just making a scheduling decision. Even if there were a process running here, the question is, did it need to continue to run in the next cell? Only if it needed to continue and I switched, would it be a preemption? So yeah, you're exactly right. So 3, because there are 3 processes that are able to run, we choose one, there's no preemption. Here, there are 2 processes left available to run in the ready queue, and we just choose one, so no preemption again. Thanks, Jay. All right. Any other questions? Let's go to earliest deadline first. So let me ask you a question just before this. Could you call this just shortest deadline first instead of earliest? Why do you think they call it earliest instead of shortest? Kind of a weird question, I know. What's that?
Depends on where you are within the period.
Absolutely, right? We're not just doing a static analysis at the beginning before you know where you are in the execution stream of whose deadline is shortest. You're looking, as you execute, you're looking who's got the earliest deadline now. It's earliest deadline first, not just shortest deadline from a static perspective. Your textbook points out EDF is a dynamic algorithm. So it's a little bit more computationally intensive as well. Justin?
Could I ask, you say what is the earliest deadline first algorithm, what are the differences?
Yes.
If you said earliest deadline first is dynamic, that would be a difference?
It would absolutely be a difference. I would look for, if I asked this question on a test, I would look for you, that would be a great answer. I would also just make sure to point out what's really driving the scheduling, right? You know, and it's kind of rate monotonic. Earliest deadline is going to be pretty obvious. It's kind of the highest priority process is the one with the earliest deadline. The name says everything. Rate monotonic is a little more cryptic if you don't know it going in, right? That's where, as Sharon was saying earlier, it's the inverse of the priorities, right? It's the shortest period first. But definitely static versus dynamic is another important distinction. Okay, so let's look at earliest deadline first and see why. You know, Stephanie was saying, well, gosh, aren't these things always going to conflict? We can see here that we can actually make our deadlines with earliest deadline first. So we start off kind of the same way. T1, T1, T3, T2, right? And then we get to here, and T1 is available again, and it preempts. Why does it preempt? Its deadline is the closest because it's down here, right? So we're still looking sort of the same, but here's where things get a little different. T2 starts to execute here because T2's deadline is first, but then T3 is available, right? But T2 continues to execute because its deadline is earlier than T3's deadline, which is way out here. And that's the critical difference between that starts us off on a better path where T2 doesn't miss its deadlines. Because it's just smarter, it's sort of a smarter algorithm. It's more computationally intensive. It's a little bit more complicated. But it's a smarter algorithm to try to look ahead to the earliest deadlines. Oh, you can ignore that. Some students last time through answered this more like a Gantt chart, a little bit more like a Gantt chart. So I just duplicated what's out there in a more linear fashion. So it would make it easier for me to understand what people are doing. So
You'll take either one or the other.
I'd prefer if you answer it like the top, because I like to give you fair grades, and I want to make sure that I understand what your answer is. And so if you adhere to sort of a convention for it, then I can be sure I understand what your answer is.
Can you please explain again? So
Sure.
the preempt starts with the preempt there, and then it continues on T2.
Yes.
Why again?
Okay, so let's take these a step at a time. For each cell that I'm in, effectively think about where your eyes are going to go. On this one, it's kind of easy. You can just kind of think about where your eyes are going to go. For this one, I get to this cell and I ask, what's the next deadline along here for a task that isn't already finished. That's really all it is. It's as though your computer had this and it was just saying, what's the next deadline for a task that's already complete? Right? And so T3 is earlier, but T3 already completed for that period. That's what's a little tricky. You got to make sure that you not only ask what's the earliest deadline, but what's the earliest deadline for a task that is not already complete for that period. All right? Okay. So, pretty straightforward. You remember the address space diagram, the components in there, heap, stack, data, code/text. There's a diagram that you can look at. Understand and list the typical elements of the process control block. So what are some things in the process control block? Program counter, register values, right? Address space locators. The address space itself isn't in the program control block, but the information on how to find the address space is. Define and provide a rationale for context switching. You guys have done that on the quizzes. You'll remember the process lifecycle state transition diagram. Just be able to complete that, understand it, answer questions about it. That'll be a lot like it was in the quiz. Understand process creation, fork, and exec. So you should be able to answer questions about it based on the slides. You should be able to look at some code and understand what the code is doing. Identify different inter-process communication models and strengths and weaknesses of each. So sockets, named pipes, ordinary pipes, shared memory, signals. You had a question like this in the exam, like this last bullet. Given a description, identify the type of inter-process communication. Any questions on any of that? Thread topics, you should be able to define a thread or recognize a definition. Make sure that you can compare processes and threads. What's the difference between a process and a thread? How are they different from each other? You should be able to identify things that are shared by threads, things that are not shared by threads. What are a couple of key things that threads do not share, for instance? Anybody think of that off the top of their head? A couple key things that threads do not share. Yep, that's absolutely one of them. What's another thing threads don't share? The stack.
Yes.
The reason I ask that is that for some reason seems to be a question that it slips the mind. So registers and stack, threads do not share them. Okay, you should be able to define a race condition or recognize a definition. You should be able to walk through a race condition scenario as you did on the first quiz. You should be able to identify some ways to avoid concurrency issues without synchronization. So we talked about that, right? Avoiding shared variables when you don't need them, for instance. So if I showed you some code with that problem in there, you should be able to tell me how to solve it. Simple code. It said, hey, how can you eliminate the synchronization issue here without, or the race condition issue here without synchronization mechanism? Okay, synchronization, recognize the different synchronization primitives and explain why they're necessary. Should be able to explain the concept of a critical section. Remember, there are 3 elements to that. You should be able to look at a critical section and say, well, yeah, that's probably well designed, or no, that's not very well designed, right? Could be poorly designed because it covers too much. It could be poorly designed because it covers the wrong things. Or it isn't, or it's incomplete. doesn't have an end, for instance. You should be able to recognize some key synchronization terms like mutex, condition variable, counting semaphore, binary semaphore, etc. You should be able to recognize some examples of specialized atomic instructions, compare and swap, test and set, that are supplied by the hardware for synchronization purposes. You should be able to identify and recognize potential problems resulting from synchronization like deadlocks and starvation. You should be able to distinguish between those two. Yes?
Doesn't starvation happen during a deadlock though too? Because starvation is when it can't get a resource. That's technically what's happening during a deadlock as well.
Yes. Starvation implicitly is something that happens without reaching a deadlock. So when you get starvation, the deadlock tasks are definitely starved, as is every task that asks for the deadlocked resources. Absolutely, you're right. But implicitly, if you're talking about starvation, it's sort of the next level up of problems of being slightly less serious than a deadlock, but still for the affected process, quite serious. But implicitly, you're still able to run. Tasks are still acquiring resources and releasing them, but there's just some task or tasks out there that aren't getting their fair share. Okay. You should be able to identify the scheduling algorithm by its description. So look at the chart in the slides that says, shortest job first, SJF. Here's the description of it. Here's its strengths and weaknesses, right? You should be able to calculate the utilization and utilization bounds in order to determine if a set of periodic tasks can be scheduled and whether that result is conclusive, inconclusive, or inconclusive as scheduling or just unschedulable.
Should we have the formula for it?
I'll provide the formula. Great question. I'll provide as you saw here, I'll provide the formula, and I'll probably provide those hints that are like, here's the most likely things that you're going to see, right? So, go ahead.
What makes it impossible?
If you ask for more CPU time than is available, usually that's represented by that. There's a part of that equation that says less than or equal to 1, right? So if it's greater than 1 and you only have one processor, then you're out of luck. You're asking for more CPU than exists in that period. If you had more CPUs, that number at the end might change, but we're not doing that scenario on the test. Okay. Explain how the time quantum must relate to the cost of context switching. You guys did great on that. Here's a question I didn't ask on any of the quizzes, I don't think, but that you might see, which is to explain CPU affinity. So don't, even though you might not have seen it on the actual quizzes, I can't remember whether it's in any of the study guides, but you should be able to explain CPU affinity and recognize the concepts of hard affinity and soft affinity. You should be able to, as we went over today, plot priority inversion scenarios and plot scenarios using rate monotonic and earliest deadline first. Okay? That's pretty much it. The test will have a lot of the same style. To Kate's earlier question, the test will have a lot of the same style you've seen in the quizzes. The questions, while they might be careful though, because some of the questions will probably be questions you saw almost exactly in the quizzes, but some of the questions might be slightly different. So be sure to read the questions carefully.
I'm assuming it won't be the same length as the quiz, but how long is it?
It's intended to be the entire class. So, all right. Thank you, everybody. Yeah. You want to come up? Yeah, so there's some slides in Sketchbook that talk about when you have more than one process. And if you look at those, what it mentions is the scheduler will actually impose some affinity for the process to run on a CPU where it started. The reason for that is the reason for that is each CPU has strings and dashes associated with it. Those are always important. But the cache isn't this straight. It's slightly larger set of more. It's closer to the front. So basically, it's just pull it in. Because the cache has got set up in the last one, and it's cheaper to access the cache. Because think about the cache basically is sort of closer.
I don't remember the whole diagram. Is it just like a draw, like for a scenario, like diagram or like
Just do a search on Infinity inside the.
I'll do that.
And you'll probably find it.
So hard affinity would be when it really wants to do it, but soft affinity would.
Something is more like a preference.
Yeah, when it's just a preference.
It's just a preference, and you can actually have load balancing that applies where it'll switch things around, right? Because as with any sort of clustered situation like that, what can happen with affinity, this is true in servers as well as CPUs, what can happen with affinity is you can overload one,
Yeah.
and so you gotta
One
rebalance.
CPU is not enough on the other CPU.
Right, and so one CPU is just not doing anything,
Yeah.
there's like 4 processes waiting on CPU one, then there's a variety of migration mechanisms to those processes.
And hard affinity is like it's a requirement.
Yes.
It needs to be on that one.
Okay,
I kind of sort of remembered that. I was just.
there was one, but just, I'll note that you were there.
Your name is your name is.
That's probably
Are
gonna
you
be
gonna
your
visit
Joseph.
me this
Okay.
weekend?
Yeah,
Oh,
I have
my
a question
cow.
about inheritance.
Eat
Sure.
my parents'
It
food.
didn't work. I actually posted that.
Study for
I
OS.
know there was that one, but I thought
Figure out
that
what's going
you
on.
can have another.
But to this
Is that
weekend should
right?
be a okay weekend.
It just showed that one posted that said
I will
they
say
have
Michelle
no
comes to my
posted
house
for
and
being
say
there.
OS. That's like
Posted that you
driving
can
2
actually
hours.
use that.
I don't know that seat.
Michelle would have to like stay in my
I can tell you
room.
that in the priority
I
area.
don't want to, it's like calling a ghost cat, right?
But can you host more than one?
Oh my gosh.
Oh,
That's
absolutely.
only like one person
I
that
don't
ever
think that
saw the
happens
ghost
in
cat,
that
okay?
scenario.
I just don't
Not
mind.
for the same resource or anything
It's
like
only
that, but
occurred
you can
once.
host,
This
you
one
can only
thought
one
I had a
resource at a
cat.
time, right?
Like, it's not a cat, like, what do you mean?
If you look at your slides, there are some scenarios where
Oh, the cat
you've
has
got
been dead.
hoisting multiple times, right? You're kind of climbing a chain with a couple of resources because one unplaced resource, it gets hoisted by the other resource, but then, you know, it comes along and it asks for a resource it can't get. So when that happens, the next process that has the other resource gets hoisted even above that, right? So look back at those slides and you'll see that. I don't think it happens in this
There
scenario.
wasn't a lot of information I could see though. It was barely anything. So,
Ceiling, I only had that one slide in there.
yeah.
Well, there's a lot of text, but I only had the one thing.
Right.
Okay.
I already scheduled my exam.
Okay.
I'm not sure, I forget what time I
Okay.
scheduled it for. I have a class right before this.
Yes.
And I like to try and do an hour between
Sure.
so I can kind of just do
Decompress a little bit, yep.
quick refresher on it.
Yep.
But I'm not sure when Jen's gonna send that email out.
That's fine. I had planned to send it to her on Monday, so,
Okay.
because that's when I'll have I'll send it to her over the weekend, because that's when I have the exam finalized.
Okay.
Okay.
Was I supposed to submit my homework on Blackboard?
Yes,
Cause I accidentally left it here with you.
she did. I picked it up. Let's double check that.
Is that a bad thing to do?
It's
that?
absolutely not a bad thing.
So I can't turn it in, or it should be on Blackboard?
No, it's not a bad, I'll take it. If you prefer to hand it in, and works out better for you, that's fine. I really don't care. Let me see, Charles. I know I picked up somebody's homework, but I just haven't looked at it. I'm not gonna look at it until the weekend.
That's me.
All right, so I got it, and I will grade it.
Now, since you're already looking at it.
Yes.
And we just talked about it.
Yes?
Yeah, I didn't get that.
Yeah.
That's how I messed. I think I messed it up here because I didn't read.
Yeah.
I
There's a
even
lot going
underlined
on in the question.
And it got me.
There's a lot going on in the question. No doubt about it.
Thank you.
Okay.
Do you have the attendance sheet?
I do here. Tell me your name again.
GUY, yeah, HO, right here.
Thank you. All right.
And the exam is going to be on
Tuesday.
Tuesday.
Yep.
Thank you.
Okay.